welcome everyone, and thank you very much for attending this webinar on Enerdata's modeling tools and how we quantify energy, your energy and climate pathways. My name is Quentin Chini. First, oh, sorry, I don't have the control of the slides. Sorry about that. So first, a few words on Enerdata. So we are a consulting company specialized in the field of energy and located in Grenoble, France, as our backdrops suggest. So we apply our expertise, our 30-year-old expertise in the field of energy and various different resources such as data science to build energy databases, market intelligence, market monitoring, market studies, and also energy modeling, which is something obviously we're going to talk about today, to provide a variety of services to a variety of clients in the field of energy. To summarize, basically, we have information services where we provide databases, energy databases, market reports, energy projections on a subscription basis for different clients, but we also work directly with different sorts of clients to provide customized services. And yeah, we also provide training on a regular basis.
Thank you, Quentin, for the introduction. My name is Aurélien Peffen. I'll just briefly introduce the agenda of the webinar. But first, let's give a few words about Quentin and myself. So the speakers of today, Quentin Chini, my colleague here, is an energy expert at Enerdata. He's worked there for about 7 years now. And he has been involved in the development of our internal modeling tools, including the Pulse Enerdata models that he will present a bit later today. And he also has experience working with power, European power market model as well. And on my side, so I'm Aurélien Peffen, and I've been working at Enerdata for about 6 years now. And I've been also involved in our global energy forecasting department, which leverages our internal modeling tools, including the Pulse Enerdata model, but also the Enerneo model that I will also talk about a bit later today. So yes, we are very happy to hold this webinar. So talking about the contents of today, we will introduce first with a broad introduction on energy systems modeling and the various types of model that exists. Then we'll dive into the tools that we use as internal expertise at Enerdata. And then to go into a more applied case, we will focus on a case study for which we've worked on the Sahel region of Africa, where we produce scenarios for a given study. And then finally, we'll wrap up and have some Q&A session. I give you the floor back, Quentin, for the introduction.
Thank you, Aurélien. So let's get started. So first, as suggested by Aurélien, we're going to talk about models and energy system models in general before we more specifically talk about our modeling tools. So first, why models? Why use models? What are models really? So in a very simplified definition of it is that models are basically a simplified representation of reality, of an actual system, and the idea is to try to depict it so in a simplified manner to be able to test assumptions and better understand how the system works, how the variables that are at play interact with one another. So it could be a tangible models, an actual maybe a small scale representation, or it could be a mathematical models, which is basically what we are talking about here. Why use models? Well, energy system models specifically, they offer actually a lot of different insights to different sorts of actors. Business actors, so companies, use models to, for example, strategize on short-term markets, when to buy, when to sell, when to hedge, essentially. Also to manage production and dispatch, and also to guide them in their investment strategies, between different investment options in a more medium to long term. Governments also rely a lot on models for planifications. So long-term energy strategies, what policies, energy and climate policies to implement, how to use their national resources, how to guarantee a secure and affordable access to energy to its citizens, essentially. But by definition, the models are limited. Firstly, because you're looking at one system that's isolated from the rest of the economy, so that obviously it's obviously a bit of an issue, and you have to formulate assumptions to represent the outside the scope of the model, and obviously these assumptions are subject to a lot of uncertainty. And the simplification itself that I mentioned, the fact that it's a simplified methodology, means that you don't necessarily 100% faithfully represent the actual real system, which also has its own limitations. Just this figure to sort of introduce an important distinction in the use of energy system models between what you may call prediction or forecasting in a very short term, when you're looking at a very short time horizon, obviously, and a pretty good grasp of how the different variables are going to evolve in this short term, right? So obviously there's always a margin for error. If you look at a weather forecast, for example, you have a pretty good idea of what the input data are going to look like, and you have also a good idea of what's the relation between the weather and these data. Still, there's a margin for error, but it's, when it comes to a projection, it's a pretty reliable type of forecasting. Now, the further the time horizon, the harder it is to formulate these assumptions, and you no longer really look at trying to give the most likely outcome of things, because you really have no idea how these variables are going to evolve, and it's mostly about building a narrative. And this is why we talk about scenarios, right? Building a narrative rather than trying to show what is to be expected. And this is mostly where we position ourselves in the long-term analysis. So energy scenarios, mostly prospective, rather than forecasting, which is a different exercise. So just a few words on the different types of models and the main characteristics of these models. This is not necessarily a comprehensive list, nor I think the distinctions between the categories are that clear, but I think it's important to introduce these particular notions. So first, very quickly on what I would call physical models. So they're still mathematical models, by the way, but the idea is to try to represent a system or a subsystem, a part of a system, in a pretty accurate way. So with a lot of technical details, it could be, for example, a transmission model where you integrate the grid with a lot of technical characteristics of the transmission lines, etc. And you're testing a set of assumptions, basically to try to assess the robustness of the model to these assumptions. There's no decision making that is made within the model. It's just, if we have this happening, what happens within the system? Now we are looking into something that we're more familiar with at Enerdata. It's techno-economic models. So they usually include very detailed depictions of all the technologies involved, and these technologies are basically in competition with each other. You're looking at, for example, a power sector model. So you have all the power plants, the existing power plants, you have all the future technologies that you can invest in, and you have to meet an electricity demand by choosing between the available power plants for dispatch, for example, which power plants to use at what time, or what power plants to invest in the future. So this is actually very valuable when it comes to assessing what can be the impact of technological changes, technological progress in electricity production, efficiency, GHG emissions resulting from the electricity sector, if we're sticking with this example. but it's usually very much relying on exogenous assumptions. Again, with the example of the power sector model, you kind of need usually from outside the model an exogenous assumption on how the electricity demand is going to evolve. Now, top-down econometric models, they usually offer a wider scope. So you no longer have this constraint. You still rely on exogenous assumptions, but much less than for techno-economic models. The trade-off is that you don't really have this, this detailed technological representation. Energy demand, for example, is expressed as a function of different drivers, for example, macroeconomic activity, energy prices with elasticities to these parameters. And these elasticities basically represent this technological behavioral changes, but in an implicit manner. They're not explicitly covered within the model. It's a problem because they rely very much on, these elasticities have been calibrated based on historical data. So it's not a very good method to, capture what could be the impact of future, game-changing technologies. Now, a few words on different characteristics. Optimization and simulation, for example, they're not really a type of model, but a methodological attribute to different models. So I'm not going to say too much about it, but basically optimization being, you have to, for example, again, to take the techno-economic example of having a power system model, you want to minimize, obviously meet electricity demand at any time, but by minimizing the costs. That could be something like that. So you rely on a solver. Obviously, this sort of means that you're not really able to capture non-optimal behavior that often happens in reality, but it's a pretty strong tool for these types of models. Now, just to introduce to our model, more and more today we have models that are not really fitting one category or the other, and you have a lot of hybrid models. That are basically taking elements of different of these different categories, and also models are often used in combination with one another to properly assess the future of energy systems. This leads me to our modeling tools here at Enerdata, and I'm going to talk a lot about the POLS model, or POLS Enerdata, because POLS is used by multiple parties, and it's one of the key tool that we use for long-term energy perspective. It's what we call a partial equilibrium model. So it's an equilibrium model, but only for the energy sector, basically, with a global coverage, and that is used for long-term assessment of energy and GHG emissions worldwide, but also on a national level. The time horizon can be up to 2070, but it's mainly used up to 2050 in the different uses that we make of it. So this is a mix, and this is why I mentioned the hybrid characteristics of model. This is basically a mix of both econometric and techno-economic models, because you still rely on this top-down econometric approach that basically gives us a level of demand by sector and this dynamic relation between activity and energy demand. But in a lot of sectors, we also include a techno-economic representation where the different technologies available compete with each other. Next slide. Okay. So just to tell you a bit more about the model. So I mentioned having a global coverage, but there's actually 66 national and regional entities that are covered, but it's actually 54 individual actual countries, plus the residual countries are put together as aggregates. This relies on an integrated approach, right? The whole energy value chain is endogenously modeled. So this really keeps the benefit of having this top-down econometric approach. We have a very large scope. If you look at the figure on the right, we basically model both national energy systems, but also interactions between countries through international fuel markets, basically. So we're really able to capture, what the global context is how the global context is going to impact the different national energy systems. Within this energy system, we're looking at, we start basically from final demand, so the different energy users in the different energy sectors for each countries, and the competition between technologies and fuels in these sectors then this has to be met by energy supply and transformation. So the demand for electricity that is obtained through the final demand modules basically has to be met by the power sector module within the model. So everything being interacting and endogenous within the model. So to do that, we need a lot of inputs. So inputs on resources available for fossil fuels and others, and a lot of assumptions. So macroeconomic assumptions, obviously, so the evolution of GDP and demographics, technology inputs, so the different costs and efficiencies of the technologies available, also historical data, because we rely a lot on past drivers within the model. And this is often some things that's key to study different variants of scenarios, energy and climate policies that we want to integrate in the scenarios. And as a result, we get consumption by sector, by energy, by use, energy production, end user prices, wholesale prices, level of investment, and GHG emissions resulting from the energy sector. Okay. All right, so just a quick word on how we build long-term scenarios, because we're going to show a concrete example of that, but in a more general manner. We usually start with a reference scenario, right? A reference case. So that could be defined in many ways. For us, it's often what we call a BAU scenario. So basically, what will happen in the future if nothing changes in terms of policies? There's no game-changing technologies that are going to have a major uptake in the system. And it's basically usually a prolongation of historical trends that we've observed, with energy demand just continues to grow with economic activity and demography. This is not the most likely outcome, but it's a good basis that is used often to quantify what is then the effort that is needed to basically attain bigger climate ambitions, for example. And from that reference scenarios, we build variant scenarios, usually focusing on a few elements for which we introduce important changes in the assumptions, basically. So it could be, it's often the case that it's just you introduce from the reference scenario to introduce a lot of different energy and climate policies, and you see what happens in the model. You can also, specifically introduce changes in the uptake of game-changing technologies, for example, EVs in the transport sector. And another alternative is that you can make differentiated assumptions on the macroeconomic framework. So you have a reference scenarios, then what happens if the GDP growth is higher or the GDP growth is lower? What's the impact on the energy consumption? When we build these scenarios, it's really important to develop a consistent set of assumptions, right? To identify what are the key drivers that we want to act on, and build a general storyline around them. It's also very important to account, and it's something that we'll see in the case study later. It's very important to account for regional and sectoral specificities within the model. Now, a quick word on backcasting approach as a way to produce long-term energy scenarios. It's something that is used more and more, where basically you start from the ultimate goal instead of trying to formulate informed assumptions on different variables. You start from the goal and you derive the assumptions that are needed to reach the goal. So if the goal, for example, in net zero emissions, you then have to come up with a consistent framework of assumptions that would lead you to that ultimate goal, where you're no longer trying to say, okay, what's the realistic evolution of this particular variable, but you're playing specifically on this variable as a lever to reach a target. Now, a few words on one of the main uses that we have of the Pulse Enerdata model, which is the Ener Future Scenarios, which is a service that is available through our as part of our information services on a subscription basis, where we basically use the Pulse Enerdata model to derive 3 different scenarios globally and for a lot of different countries. I won't spend too much time on this. I will directly show you a slide about the results of these scenarios. And our vision of the future of energy systems globally is derived into 3 different scenarios. So Enerbase is, what I referred to earlier as a reference scenario. It's just, existing measures, and it's mostly an extrapolation of what we've seen historically, with few to little to no improvement in terms of carbon intensity, for example, sort of the amount of carbon emissions related to economic activity. Blue is an intermediate scenario where we've included basically all the emission targets from the nationally determined contributions. And then Green is an even more ambitious scenario where we basically more of a backcasted approach of trying to limit the temperature increase below 2 degrees Celsius, right? So you can see in the different graphs the major differences between scenarios. And if you look at the table here, you see that aligning with this objective of reducing or limiting the rise of temperature means huge, completely, very important, significant changes in carbon intensity here. So this is percentage per year. So we would have to reduce globally our carbon intensity by 7% per year to be able to reach this particular target, for example. Now, very quickly, a few takeaways from Future that I think are quite interesting to look at. Emerging economies are going to be the key to reaching these targets, basically. As you can see in the chart on the left, non-OECD countries account for 3/4 of basically abatement between the reference scenario and the Green scenario, right? That doesn't mean that it's a bigger burden for non-OECD countries. It's just that they will represent the biggest share of emissions by 2050 in the base scenario. Therefore, they're going to have to contribute a lot in absolute terms. In relative terms, OECD make basically a bigger effort. That's what you see actually on the right, right? The carbon intensity for OECD countries, which is the bottom green one, is close to 0, basically. Whereas the non-OECD countries, you see a convergence, obviously, but it's a bit higher. It's also important to keep in mind that there's a lot of co-benefits, on top of saving the planet, which is a clear one. There's also decarbonizing is also a way for a lot of countries to reach, for example, energy independence by not relying on fossil fuels, which are often for a lot of countries that don't have a lot of resources, but that are going to have a huge economic development. They import a lot of energy. So decarbonizing and switching to renewables, for example, is a good way to guarantee having less reliance on international imports. Another big takeaway is the role of electricity in this scenario. In these, in the deep decarbonization pathways, such as Green. So the idea is that electrification is an important feature of these scenarios, but only if you're able to decarbonize the power production, right? So switching to electricity while decarbonizing offer a lot of abatement. And it's also often leading to significant energy efficiency improvement. That's the case, for example, for electric vehicles or for heat pumps and that sort of thing. So it's a key element of these scenarios. And it's achievable in a lot of uses, but it is also limited from a technological standpoint, because you would need to rely on very innovative technologies in some sectors and some energy uses. And this is why you have to promote electrification while not neglecting other key drivers to decarbonization. For example, all the demand side measures, so energy sufficiency, energy efficiency, and also gas decarbonization, for example, are also key elements, right? It all comes together. Now, just a quick word, because I think I'm running quite late. Just a quick word on other main uses of our models, with, for example, here the production of marginal abatement cost curves. Basically, by leveraging the post-Enerdata model, we are able to, I don't know if you're familiar with the concept, but basically producing max. So relating the level of abatement to a price of carbon. Basically, as you can see in the graph on the left here, you have total abatement reached for different carbon prices. So we basically introduce a carbon price in the model, and we see what's the abatement observed in the different sectors. We are also able, using a tool that we've developed here that is called Aero, we are also able to then break down this abatement by different technology options. So the two charts at the bottom are representing abatement in industry sector. So you see the total abatement reached for different years at different prices. And then on the right, you have the breakdown into different options. So the role of different technologies and different options for activity, the level of electrification and how it impacts abatement, fossil fuel switching, which is quite marginal here, efficiency in industrial processes, so lowering the carbon intensity, and also on top, the role of CCS in reducing abatement. So yeah, so one of the key outputs of this combined use of the model and this additional Aero tool. Now, a quick word which will serve as a transition to the next step, the next chapter. A quick word on Enerneo, which is basically using the logic and deriving from the Pulse Enerdata model that I introduced. We've created a national level, or actually it could be also regional level, but just a different, not a global geographic scope. We created this flexible tool that allows to do energy scenarios with a lot of the features of Pulse Enerdata, but using Microsoft Excel, which means that it's really easy to transfer to clients and different users. But it's really matching the methodology behind Pulse. So I'm not going to say too much about it, and I'm going to let Aurélien present a specific case that is using the Enerneo platform.
Thank you, Quentin. Okay, let's now dive into a case study that we did on the Sahel region. Just to give you a bit of context first, we supported the IEA, the International Energy Agency, as part of an initiative which aimed at producing a report named Clean Energy Transitions in the Sahel that I definitely recommend you look afterwards, because it's really comprehensive and very insightful. And the idea of this study was to analyze the current state of development and recent trends in the Sahel region, and then exploring two scenarios to 2030 and understanding what the next steps for energy in the Sahel could be to this horizon. Basically, the final aim for the IEA was to leverage this analysis to identify policy recommendations, best practices, organize workshops with officials from the countries, etc. And so we contributed to this study by contributing to the production of the Outlook to 2030, so the scenarios, right? That's where we supported the IEA. And I'll get back to this point a bit later to understand how our contribution was needed and how we were able to match the needs of the IEA. But first, in terms of geographical scopes, what we call the Sahel in this case is the aggregation of 6 countries, which are listed here: Senegal, Mauritania, Mali, Burkina Faso, Niger, and Chad. And just a side note that for the modeling part, as there are discrepancies in terms of development in the countries, and Senegal being a more advanced economy than the others, we split the geographical scope between Senegal on one side and the rest of the region called G5 Sahel on the other side. So 2 models for the scenarios. And so this study dates back from 2021, and it has been followed by other studies from the IEA on other regions, including the Horn of Africa, for instance. So if you're interested in other geographies, look it up. You will find some additional material. Before going into our work and the production of the Outlook, let's give you a bit of context on the region. So the Sahel is this region between the Sahara and the savannas to the south, and it holds a population of about 100 million people in 2019, with a fast-growing trend. Basically, it has doubled since 2000, and the fertility rate is high, with the 5 breaths per woman, which is higher than the African average, basically. So basically, the population outlook is still increasing quite significantly, and we expect the population to more than double by 2050. In terms of economic growth, the GDP growth in this region is also quite high, with over 5% per year since 2000, which is a fast-growing economies. This being said, the level of development of these countries remains low. If we look at GDP per capita, for instance, the average of the region is close to the Indian average, and it's 15 times below the EU average. So that this is low. Keep in mind also, as I mentioned, that there are significant discrepancies between the countries of the region. For instance, Senegal has a GDP per capita over 2 times higher than Chad, for instance. So not a homogeneous GDP, level of development in these countries. In terms of energy consumption, which is one of the main topic that we studied, we can see that the final demand of the region is low. It's 18 megatons of oil equivalent in 2019. That's more or less like Switzerland. And remember that there are 100 million people in the Sahel region, whereas there are only 8 million in Switzerland. So this is quite low, and households consume most of this demand for cooking purposes mostly, with traditional biomass remaining the major fuel there. Basically, wood-based traditional biomass represents maybe 85% of the household consumption. We see a small development of electricity, especially in the recent years, but it remains low with 5% of the demand. We can also see that the consumption of fuel for transport is increasing rapidly, and it's actually one of the main drivers of oil consumption in these countries. Industrial energy consumption is quite low in the region, and it's mostly used for mining companies. There are some resources in these countries. Looking at the power sector now, so we've seen that the electricity consumption is starting to increase, both in households and in industrial uses, and this translates into a very quickly increasing power generation. It has been multiplied by over 4 since 2000, but there are still also here some disparities across countries of the region, with Senegal being far more electrified than other countries of the region, for instance. We can also say that probably the electricity demand, is mostly concentrated in the city and in the urban areas, where the connection is cheaper than in rural areas, where the cost of expanding the network is quite prohibitive for these countries. And in terms of energy supplying this electricity, most of the power plants are oil-based, so using fuel oil and diesel. But it starts to change and to diversify in the past years, with coal power plants being opened in Senegal and Niger, and some solar installations starting to be to come online in the past 5 years. We can also cite the fact that there is some hydroelectricity resources in the region, especially in Mali, but this is still quite limited and will not cover most of the future increase in power generation. If we look at CO2 emissions, well, obviously, as we've seen, the oil use for power generation and transport has increased quite a lot in the past decades. So the CO2 energy emissions, which are the emissions related to the fuel combustion, basically, they have grown quite quickly, 7% per year. But let's keep in mind that the average emissions per capita, they remain very low. We have 0.3 tons of CO2 per capita, which is definitely very, very low. If we look at sustainable development goals, which is one of the key aspects of the study, one of the key focus points of the study, and especially the 7.1 Sustainable Development Goals, which is the access to clean energy, basically. Well, we see that the access to electricity, so the number of households connected to the grid, basically, or having power, access to a source of power, it has progressed. It has doubled actually since 2000, but it still remains low, 32% in 2019, which is quite low. So here again, as I said, Senegal is far above other countries of the region with 70%, and Chad lags behind with 8%. The other indicator that is quite important to look at is the clean cooking access. So this is access to modern cooking solutions and not traditional biomass, and it is stagnating since 2000 at around 10% of the region. So this is an issue because combustion of traditional biomass causes problems of efficiency first, but also air pollution near the cook stove, and also it requires a lot of time to gather the woods, etc. So this is a major issue for the region. And then if we look at renewables as well, well, if we exclude the traditional biomass from the count, well, basically the share of modern renewables is almost non-existent, with only 2% of the consumption. I think that was just to give you an overview of the context in the Sahel. Now, this brings us to where we contributed to the study, which is the outlook part, the part where we created scenarios. So the IEA needed to produce some scenarios for the Senegal and for the G5 Sahel with dedicated modeling tools. The problem with that is that the IEA obviously has internal modeling tools, including the World Energy Model that you might know, which is used to produce the World Energy Outlook, for instance. But this tool has a global coverage, but it does not allow a flexible geographical perimeter, which is something that our Enerneo model brings. And that's why we found that Enerneo was very suited to treat the topic of this study. So what we did was use Enerneo, create two versions of Enerneo for the Senegal on one side and G5 Sahel on the other side. We incorporated historical energy balances from the IEA, energy consumption, productions, etc., which is needed to run the model. And the IEA, obviously for consistency issues with the historical analysis and the projections, it was only logical to integrate the energy data from the IEA. Then we completed the model's input data set for other variables using various data from IEA, from our own data, and also estimations. And then we also refined a bit the modeling of the model of Enerneo by adding some indicators about electricity access and clean cooking, just to be sure we match the need of the study. So that's also one way that the Enerneo model is flexible enough to take into account project-specific constraints. And so then we were able to use Enerneo to produce the scenarios, create the results, and then the IEA exploited our results to write the report, basically, that I presented earlier. A quick word on the definition of the two scenarios that were developed for the study. So we have a stated policy scenario, which is called STEPS, and which is really aligned with the usual STEPS scenario from the IEA. So if you're familiar with those, for instance, in the World Energy Outlook publication, it's the same approach, which aims at taking into account the policies and plans from the countries, and not necessarily their pledges if they are not backed by concrete policies, basically. So that's the spirit of this first scenario. And then the storyline for the Africa case scenario includes a more rapid economic development, and also, and most importantly, universal access to electricity and clean cooking in the region by 2030, which is in line with the vision of the African Union. But this is a huge assumption, as we've seen earlier. this translates into increasing significantly the rate of access to electricity and even more for clean cooking, basically. The idea of the scenario is also to enhance support to renewable technologies and foster energy efficiency to maintain CO2 emissions relatively in line with the stated policy scenarios, despite a higher economic development, basically. If we look at the GDP assumptions, well, basically, as you can see on the left graph, we have a higher GDP assumption for the Africa case scenario, which is about 0.4% per year addition of economic growth, basically. As for electricity access, we had a similar assumption actually for Senegal, with universal access reached in both scenarios, because there is a plan in Senegal aiming at this universal access by 2030. And for the rest of the region, well, the trend in the stated policy scenario would lead to 32%, and we would reach universal access in the Africa case. Let's look quickly at the results from the analysis. In the stated policy scenario, in terms of access to electricity, there are still around 80 million people who lack access to electricity in 2030. So that's only 41% average access rates. Whereas in the Africa case scenario, as I just mentioned, we achieve universal access, which means basically connecting 8.5 million people every year to a grid or a mini grid, or installing, standalone power systems. And this translates definitely into a much higher electricity demand in the building sector, as we can see on the right-hand side graph. And we'll see that this has a large impact on the power systems. We can see that already in the stated policy scenario, we have 10% per year increase in the electricity generation, and this is even much higher in the Africa case with 15% per year. So this compares to about 7% per year historically. So we can see that it's slightly, slightly faster in the stated policy scenario, and it more than doubles compared to historical trend in the Africa case scenario. In terms of mix, we can see that the oil products-based generation is decreasing in both scenarios, and the capacity additions are mostly coming from gas-fired generation and solar PV. So obviously, given the potential of solar PV in these countries, it's a strong candidate to develop the electricity generation systems of these countries. If we look at clean cooking, which is the other big indicator that we wanted to look at, in the stated policy, we still have 120 million people by 2030 lacking access to clean cooking equipment, whereas in the Africa case, we achieve universal access, which means 12 million people per year gaining access. If we look at the final demand in the building sector, where cooking is the most important use, well, we can see that traditional biomass declines much in the Africa case scenario, especially, and considering the fact that it's highly inefficient to use traditional biomass when compared to more modern solutions, we can see that the total final consumption in the Africa case is much lower than in the stated policy scenario, basically. And it is displaced by both LPG, electric cooking equipment, and improved modern biomass cook stoves. So three alternative technologies, and it also depends on the countries, with LPG being especially fostered in Senegal and Mauritania. If we look at the other sectors, notably industry and transport, we can see that the additional developments, which was also included in the model in the form of additional economic growth, is balanced by additional efforts in terms of energy efficiency. That's why we see on the graph for industry on the left side that the final energy consumption is not much higher in the Africa case than in the stated policy scenario. And in the transport sector, it even leads to a slightly lower consumption in the Africa case when compared to the stated policy scenario. And for that, we even did a small breakdown of the various effects. So here, what we look at is the stated policies scenario consumption in 2030 on the left bar, 5.8 megaton of oil equivalents. And then we can see the various effects that impact this consumption to reach the Africa case value. We can see that the additional development in the Africa case scenario tends to add, all things being equal, it tends to add a consumption of about 0.7 megatons of oil equivalent, but this is compensated by additional efficiency in the motors and having more efficient vehicles, and also a small contribution of the electrification of the fleet, especially for two-wheelers, basically. And that's how we end to a slightly lower consumption in the Africa case. Maybe a last slide to give you a big picture about the CO2 emissions. So if you look at CO2 emissions, we obtain slightly higher emissions in the Africa case, but both are pretty close at about 55 megatons of oil equivalent. So additional efforts towards renewable energy, especially in power generation and energy efficiency, enable to limit the increase in emissions that we could have expected given the higher development in the Africa case scenario. A quick note that also in the Africa case scenario, we reach much higher electricity access and clean cooking access, which also implies a switch from traditional biomass to LPG, generating emissions. And that in the step scenario, this is not the case. Which brings me to the next slide, which is an exercise that we haven't conducted, but which would be very interesting, is to look beyond 2030. So the model could allow to do that. It was out of the scope of the study, but definitely a good question. So considering in the Africa case scenario, the transition towards sustainable development has been reached much faster. What we could assume is that basically afterwards, additional efforts toward renewables energy efficiency would help to curb the curve of emissions, as we can see in orange on the graph. Whereas in the stated policy scenario, there would be a continued push for electricity access and clean cooking, meaning a switch from traditional biomass to LPG, meaning additional power generation, and probably the emissions in the long term would then be much higher in the stated policy scenario than in the Africa case scenario. But this is just an intuition, right? And what we would need to do, basically, if we wanted to quantify these effects, would be to use the model to confirm that. I hope this was a good illustration of how we can leverage one of our tools, adapt it, and apply it on a specific case. I give you back the floor, Quentin, for conclusion.
Yes, thank you, Aurélien. I'll try to wrap it up quickly so that we can get to the questions, because we do have some questions here. Can you switch to the next slide? I don't think I can ask for the control of it. Thank you. So we've presented a concrete example of how we deal with these energy projections in a very specific context, and how we have to sort of try to better understand the context, the historical drivers, what are the key variables at play, and try to produce a robust analysis assessment. We do have obviously a lot of tools and amount of expertise inside Enerdata that we use to do various approaches. So this was a specific case, but we have a lot of different services that we can provide off-the-shelf scenarios, such as Future, customized scenario where we work directly with clients to produce scenarios, integrating a lot of their assumptions and their vision on a specific country, region, or globally. And we do a lot of, in general, capacity building for clients, so either training or delivering directly. And I think that answers one of the questions, actually, delivering directly to clients tools in order for them to develop, and training in order for them to develop the expertise and these capacity in-house. We also, to cover what we do not cover with our existing tools, we also work with a network of partners that enable us to have a real complete coverage of energy systems and their impacts on climate. So if we can, go to the last slide, just a wrap up of the agenda, and we can switch to the questions. So I think maybe start with the questions specific to the Sahel study, and I'll ask you a couple, Aurélien, and you can address them. So first of all, a question was, what was the drive to make this study, particularly in Sahel? What are the resulting emissions in the two scenarios? And how do you think the current energy crisis and the gas prices that we have would affect this work, given that it was obviously performed before that?
Okay, thank you for the questions first. I'll start by the first one, which is what the drive to produce the study. And I think the drive is for the IEA to engage with countries in Africa, and it's an effort that they are continuing currently. The idea is to engage them, to support them with policy recommendations, training, capacity building, to envision the planification of their energy systems, and to capture the interactions between development goals, which, for instance, electricity access, etc., but also other co-benefits of energy transition. So the idea is really for the IEA to engage, to organize workshops with officials from the countries and discuss these issues. But I think if you're interested in this effort, feel free to look at the study online, and you'll find a lot of information about the work of the IEA. So the second question was about resulting emissions in steppes in Africa case, and I've showed a slide. So I suppose this was before I saw the slide, the resulting slide in terms of emissions. And the third question was the impact of the current situation, recent developments on the study. Obviously, we have done the study more recently in the Sahel. So first of all, we would have had more recent historical data, so less, a lower projection period, which can change some of the trajectories. And also, obviously, the gas prices would have an impact in the model. So the international fuel prices are one of the variables of the model, which impacts in turn the demand and the split of technologies in the different sectors. So hard to say exactly what the impacts would be, because that's where that's what we use a model for. But yes, we could definitely anticipate a lower share of natural gas in some sectors.
All right. Thanks, Aurélien. I will take a couple on the tools in general and polls. So polls was meant to take into account the European markets interconnection, as well as wholesale prices, market price shield, etc. So kind of an insider question here, but I think as a general answer, yes, this is something that we have in mind that I think we're lacking. Europe being kind of specific in the way that it's really an integrated market of different countries, whereas polls has more of a national view of energy systems that are then connected to each other, and I think there's a built-in constraint that prevents us from dealing with the interconnected markets in Europe. And I think this is where we would probably more go towards a coupling of different models as a solution to these sorts of issues. And I think that also answers a couple of questions that I think that there's a limit to what you can cover within a single tool, and we're going into the direction of trying to couple, whether it's power system models with a high granularity, being able to look at flexibility, for example, in a way that's more detailed than Pulse is doing, or interconnected markets with a limit, limits from interconnectors on how to supply the whole of Europe. So this is I think where we're going towards, and it's the same thing. I think there was a question on adaptation and how we cover that, I think that this is a similar thing, that we cannot have everything integrated into polls, but we are looking to use the results of other models or couple different models to be able to take insights from these specific issues and integrate them as inputs into polls, and maybe have an iterative approach as well, because obviously the two are interconnected, right? So I hope this answers these questions. One question about how we model the behavior, this is kind of a specific one, of the OPEC cartel, and how do we handle potential regressiveness of climate policies. So on the OPEC side, there is a limited account, like endogenously in the model, of how the OPEC behaves, but mostly as a balancing producer, and you don't have at least explicitly modeled the role of OPEC, for example, in the production quotas and that sort of things, to be able to maintain a high price. But that's something that, again, we can integrate as an external assumption. What do we want to assume in terms of what will be the impact of OPEC behavior on the price? That's also built into the parameters. So price, the equation that drives the price in the model, is supposed to include OPEC behaviors based on historical regressions, but I'm getting a bit technical here. I'm not sure I understand. Maybe you can rephrase that on the potential regressiveness of climate policies. So maybe you can rephrase that part.
I think there's another question, which is for cooking equipment. There was no historical progress, despite governments being interested in fostering improvement of cooking equipment in the Sahel. So how did we end up projected to universal access? Basically, that's one of the questions. And I think it's quite interesting because it relates to what you explained at the beginning. We are not doing some forecasting scenarios. Basically, we are trying to build a storyline and to understand what does it take to reach a certain target. So, for instance, if we are talking about universal access to clean cooking, we did the scenarios to understand what the implications of these targets would be in the various sectors. And what would it take to do that? And that's where the IEA leveraged our analysis to then derive some policy recommendations and best practices from also other countries. So it doesn't mean that the Africa case scenario is the most realistic one, but then it helps to set a cap and to understand what a possible pathway could be, basically. And I think it maybe correlates to the question about regressing policies. It's what we are trying here is to build some storylines, and we didn't have any need for a scenario where policy would regress, but this is something we could do if we felt the need to, basically.
Yeah, and there's only a limited amount of set of assumptions that we can test. This is why when we do these projects, we usually try to have a range or representative scenarios, but obviously there's an infinite number of alternatives that we could be assessing. And this is why when we worked directly with clients, we try to integrate variants that they want to personally try to model. I think we're reaching the end. Maybe we can take a few questions more, but otherwise, if we're not covering your questions, because there's actually a lot of them, we can take them offline and basically send some answers to these questions afterwards by email to all the participants.
Yes, I think I can just take a final type of questions. There were a lot of questions about NRNEO, what NRNEO is able to capture, model, etc. So I won't go into the details of every questions, but basically let's keep in mind that the way NRNEO has been built is to be flexible and so the starting point is the polls methodology, basically, which enables to capture given perimeter, a given scope, but it's always possible to refine the tool, as we have done for these clean cooking indicators, for instance, for this Sahel study. So it's always possible to take the NRNEO model and enhance a given sector if it's needed, to be able to capture the effects that are required for a specific case. I won't go into further details for the particular questions, but just an important point.
Yes, thank you. I see maybe one last question at the top on, you know, our scenario being a 2-degree compatible scenario, whereas, you know, 1.5 is now agreed to be the target. I mean, it's first of all, it's below 2 degrees. It's kind of difficult to conclude exactly on what's going to be the impact on temperature, because we're only looking at energy systems. So it's a lot of benchmarking against other sources and what the IPCC has been doing. And we are being cautious, you know, in the definition of the scenario. It could very well be in line with a 1.5 degree if we wanted to go, because it's, you know, this extra abatement that you need from a 2 degree to a 1.5 is actually the harder to deal with. And this is why, you know, even the IEA, when they do the net zero scenario, they don't give the details per country, because it becomes a bit you know, complicated to assess. So yeah, we're going into that direction, and I think in the near future we'll be able to propose a consistent scenario which is compatible, explicitly compatible with the 1.5 degree temperature rise.
And just to add to that, it also really depends about the post-2050 trajectory, right? Which we don't cover as
exactly.
part of our
so not only are we only covering the energy system, but the temperature rises up to 2100 basically. So there's a lot of, you know, a lot of different trajectories could lead to the same temperature rise theoretically, trajectories up to 2050. So it's kind of difficult to interpret. Okay, I think we'll leave it there, but I'm pretty sure that we will be able to you know, to give a write-up with answers to the questions that we haven't been able to address. So sorry about that, and thank you very much for attending. Yeah, have a good day, everyone.
Thank you for attending. Bye-bye.
Bye.